Welcome back to Pratik Academy. In last video, we have started numericals on energy analysis methods for vibration analysis methods. In this video, we have also continued that part. So consider first numerical. Okay, then is the arrangement, and for that arrangement, they have asked to find out natural frequency. It is Fn or omega n for system. So first see this arrangement. In this arrangement, one mass is attached to string of length L, and this string is attached to or connected to one spring having stiffness K, and this spring is at a distance A from support. Okay, then at any instant, if we deflect this system by amount say theta, then in direction of motion it will get accelerating torque. Okay, but when it deforms in this direction, there will be restoring forces developed. First restoring force is developed due to its mass. Okay, at an instant, one component of weight will try to move in its equilibrium position, and again there is one spring which is moving or try to move this system to its equilibrium position. So here we are applying Newton's method. It is accelerating torque is equal to restoring torque here. Then accelerating torque is single one, it is due to acceleration, so it will be equal to I theta double dot. But restoring torques are two. First restoring torque is due to spring force at a distance A, and second is due to weight at a distance L. Okay, so first find out what is the spring torque. So spring is at a distance x. When mass deflects by amount theta, then this distance is a, this distance will be a, then this deformation will be arc subtended is equal to a theta. So restoring force will be k into deformation is a theta, so k a theta will be spring force generated at a distance a. So restoring torque will be k a square theta. K a theta is force at a distance a. Then next is restoring force due to mass. Mass it attached at this point. This point weight is always in downward direction. We can divide this weight into two components. This component will be mg sin theta. This component will be mg cos theta. We have seen in application of Newton's method for transverse system. We have seen this. Now for small deformations, mg sin theta will be mg theta. So restoring force will be mg theta, and it is at a distance L. So restoring force due to mass will be mgl theta. And this is the third equation. Putting these values in equation 1, we get restoring torque I theta double dot is equal to minus k square plus mgl theta. Minus indicates both are in opposite direction. Adjusting term here, then I is the mass moment of inertia of this mass, as this string is massless, so total mass of system is at m, so its I will be ml square here. Then arranging in standard format, it is standard format is theta double dot plus omega n square theta is equal to 0. So arranging in this format, we will get omega n square is this term, so natural frequency will be under root k square plus mgl upon ml square. This is the natural frequency. Okay, this is a simple one. Now let's take next problem. Okay. So again, in this problem they have asked us to find out natural frequency. First consider, let's check what is the actual arrangement. Here there is a rod which is connected to one spring at extreme level, and at some intermediate level A there is again mass it attached with spring here. Then as seen in last video, there are two springs having its own individual deformation. So here we are using equivalent deformation system or method. Now consider if del is the deformation of mass, then this deformation is due to deformation in spring K2. It means if there is a del 1 deformation is there, then this mass will be amount deformed by amount del 1. Or what is the deformation in K2 spring totally added to deformation or movement of this mass m. Okay, so here there will be del 1 for spring K1. It is at distance L. So when this spring is deformed by amount say del 1, then our mass will deform by small amount del, not equal to del 1 here. So total deformation of mass due to deformation in spring, if del 1 and del 2 are deformation in individual spring, this del 1 is deformation in spring 1 separately, del 2 is deformation in spring 2 separately, then deformation of m is del 2 plus this del, not del 1. So deformation of mass is equal to del 2 plus del, then del 2 plus these two triangles are similar triangles here. This triangle and this triangle are similar triangles, so we can arrange del upon del 1 is equal to del upon del 1, and corresponding sides are a upon l. So del is equal to a upon l into del 1 by similarity triangles. Putting this value here, we get a upon l del 1. So this is the relation for deformation of mass. Now consider forces acting. As this rod is weightless, so mass acting on or force acting on spring K2 will be equal to weight of this spring. Okay, force 2 is will be weight, but this spring is not above exact above this spring, so force is not equal to F, and we have to use calculate this force by using moment. Then moment about at this hinge at any instant will be moment due to this mass at hinge A or hinge O here is equal to F into distance A. So F1 into L, spring is at distance L, so if F1 is the force in spring 1, then F1 into L here will be equal to F2 into A. This distance is 2, then F1 is equal to this F2 is weight of mass, then W upon L A. So F1 will be W A upon L. So putting this value in del 1 equation, del 1 will be F1 upon K1, that is W A upon L K1. Now putting this del 1 values and del 2 values in equation 1, we get del is equal to W upon K2 plus W A L K1. This is force, the force, sorry, W A L K1 into A upon L. Okay, now solving this, we get here del is a deformation of mass or equivalent deformation of mass. This can be replaced by W upon Ke here, and then cancelling common terms, we get 1 upon Ke is equal to this. Arranging, finally we get equivalent spring system is equal to K1 K2 under root upon K1 plus A upon L square K2. So important point is here, as both springs are attached separately, deformation of mass is not exact equal to del 1 plus del 2, but we have to consider resultant deformation at above exact above of this mass due to spring at a distance L. Okay, this is the problem. Now we'll solve another problem here. Okay, simple U-tube manometer is filled with liquid and calculate frequency of vibration. Here we are again using total energy method because it is a simple one. Total energy is constant, that means kinetic energy plus potential energy at any instant of system is constant. Kinetic energy is nothing but mv square. Suppose, sorry, initially suppose we deflect this water column by amount x, then it will deflect by its equilibrium position and it will start vibrating about this equilibrium position. So here mv square is equal to 1 half m x dot square. Then mass, suppose rho is the density, given length is L, A is the area of this tube, then mass is equal to rho into volume, so that will be rho L into A. So this is the total mass of system, rho AL to x dot square. Then potential energy, or when you can calculate potential energy, we are considering change in potential energy. So the deflected mass is x here, okay, length of water column deflected is x here. So while considering potential energy, we will consider mass in only that x column. So here we are considering x, so our mass or equation is mgx, then m is within this deformation x, so it will be rho ax into gx. So change in potential energy will be rho a gx square. Then putting in equation 1, we get potential energy plus kinetic energy plus potential energy is equal to constant, differentiating with respect to t and equating to 0, we get this. And now arranging or collecting common terms, here it is not required, then cancelling common terms, our final equation will be lx double dot plus 2gx is equal to 0. Then arranging in standard form, that is x double dot omega n square x equal to 0, we get natural frequency is equal to under root 2g by L. This is the last problem from this type. So in this video it seems that problem is not understanding. If you have some doubts, then we have provided our contacts, can message us, WhatsApp us, we will try to solve your problems. Thank you for watching.